Nice. And let's finish 4.7, and I'll kind of give you a rundown of what expectations are. Next. Come on. I had to raise it up because I'm super tall. Makes sense, right? All right, sweet. So on 4.7, okay, this is all the work for letter G, the very last one on 4.7. If you were in the second hour, you got this. If you're in the first hour, you did not. And I don't know when you showed up or when you were doing this last week. It depends, obviously, because not anyone was here. But so for G, what I gave you was two aqueous reactants, and what these are both ionic compounds. We're going to flip-flop partners, and then we're going to get an aqueous product and a solid product. I told you that one of them was going to be a solid on purpose so that you could recognize that it's precipitation. Okay, so to recap this assignment, the whole goal of 4.7 was to hopefully identify different types of chemistry going on. We had 4 reactions that I hope that you can maybe identify as we go forward this school year. Combustion. Combustion is pretty easy to find because it's just some carbon molecule plus oxygen gas giving you carbon dioxide and water. We have acid-base reactions. There's 2 types of acid-base reactions that we have to be on the lookout for. The first one is just the normal, that molecule has H, that molecule has OH, acid-base reaction happens. Then we have the Bronsted-Lowry acid-base reaction where one reactant transfers a proton or a hydrogen ion to the other reactant, okay? And then we have redox, and we have precipitation. So there's 4 reactions that I'm hoping we can identify. The notes in this sheet should help you quite a bit. You're kind of looking for various little indicators to tell you what kind of science you have going on. I think redox is the hardest to identify, but you can use process of elimination to figure out its redox. That's one option. Or eventually, once we get back from break here, we'll do a whole bunch of redox so that you'll probably feel much more confident on it and a little better in terms of finding what you need to find. So anyway, this is a precipitation reaction. The products of this reaction, again, we're just flip-flopping cation with anion, right? So these cations will just go with the other anion, so to speak, to make our products. And when that happens, I'm telling you one is solid, and I'm telling you one's aqueous. Now the question is well, which one is which, right? Is the ammonium nitrate or the barium phosphate going to be my precipitate? You have a solubility chart on last year's periodic table. That's an option. Or, generally speaking, there it is. Or you can look at this little list. Okay, if one of your products contains sodium, potassium, ammonia, or nitrate, that is going to be aqueous 100% of the time, every single time. So be on the lookout for these 4. If you see something with one of these 4 ions, okay, it's aqueous, guaranteed. Doesn't matter what it's with, it will be aqueous. So in this case, we have 2 of them. This is aqueous no matter what, that's aqueous no matter what, and if they're together, well then it's extra aqueous no matter what. Has to be. Okay, which implies that the other one is our precipitate. Now, this is the net ionic. With net ionic equations, just to refresh our brains, what you do is any aqueous ionic compound, like these 3, when they're added to water and they are aqueous, they dissociate. They don't exist as molecules together. They exist as molecules broken apart. So this gets written out like such. And you'll notice the quantities here, right? Because 2 times 3 is 6, so I need 6 ammoniums. 2 times that just gives me 2 phosphates, 3 bariums. 3 times 2 is 6 nitrates, so on and so forth. The precipitate on the solid or on the product side does not get dissociated, right? It's solid. Solids, liquids, and gases are never dissociated. They are together always. It's only the aqueous ones that we dissociate. If it's an ionic compound that's aqueous, we break it apart. So we get some spectators, and then what's left is our net ion. Okay, so that kind of wraps up 4.7. Now, let me give you my roadmap for 2 days of school. What I want is to finish 4.8. We're not going to finish it today. No chance. We're going to finish it sometime tomorrow. I don't know if that's going to take me the whole hour, half the hour, just a little bit of the hour. We'll see. But I'm not going beyond 4.8 in the next 2 days. Okay? So sometime between today and tomorrow, we're finishing 4.8, topic 4.8. By the end of the day tomorrow, your homework assignment, homework unit 4, topic 2 is due. And once we learn all the 4.8 stuff, you have all the tools that you need to answer all the questions on there. But that's the next 2 days. We're going to finish 4.8, and we're going to finish our homework assignment, and then we'll call it a break. I will have no homework for you over break. Okay? We'll come back. We'll do 4.9, which is a whole bunch of redox stuff. We'll review. We'll test. 4.9 is the last topic in unit 4. Okay? That's the plan. So, without further ado, let me switch over and let's do 4.8. All right. Okay, so 4.8 is all about acids and bases, more specifically the reactions and a couple other little minutia that we need to define and figure out. But I'm going to start with the review, okay? And what I want is for you to think about these 2 questions. What do you remember about acids? What do you remember about bases? Okay? And if you could, jot something down. This goes for you guys at home too. I've only got 3 people in front of my face today. So if you're at home and you're willing to participate, I would greatly appreciate it because I don't want to put everything on just 3 people. But anyway, write something down, please, in each of those columns if you could. What do you remember? Anything. I don't care what you write, as long as it's relatively, important for an acid or a base. Write it down. I'll give you a minute head start here, and then we'll start talking about it and jotting down a list as a group. All right. So, what do we remember about acids? What do you got for me?
When they dissociated water, it produces H1 plus.
Yeah, that's the Arrhenius definition. What else do we know about acids? Or bases, I suppose. I'll just open it up. I don't care which side you're going on here, but what else do we know? But either of these. And folks at home, feel free to unmute and participate. What else do we know about acids and bases? Yeah, that's the Bronsted-Lowry definition, right? So acids are proton or hydrogen ion donors. What else? That's it.
Acids have a low pH.
Nice, thank you. So low pH, I'll say less than 7, right? Yeah, we can start filling in the opposite of these, right? So why don't we just do that? Acids produce H1 plus. What do bases produce? Yeah, hydroxide. Okay, so dissociate in water to produce hydroxide. Okay, bases are hydrogen what? Hydrogen acceptors. And if acids have low pHs, then bases have high pHs, right? And we'll define that as greater than 7. Other acid-basey things, it doesn't matter, anything. What else do we know about acids and bases? This is a good start. And that sounded like Gavin, by the way, so I appreciate your participation. What else? That's it?
Could you say acids don't turn like phenolphthalein any color or like stuff like that?
Sure, I'll take it. Phenolphthalein. Okay, if it's an acid, it's colorless. If it's in base, it's pink. Yeah, absolutely. Thank you. I don't know who that was, though. I apologize. I'm not staring at my computer, so I only hear voices in my head. I'll get that checked out over break. Okay, what happens when you mix acids and bases together? If I mix an acid with a base, what happens? Silence. That's what happens. Acid, base, then what? What happens? You make water and salt. They neutralize one another. So I'm going to write it generically like this. A for acid, B for base, and when these react, I get water and salt. Okay, that's the generic setup of an acid-base neutralization, right? I think this is a pretty darn good list. There's a couple other straggler things. If you wanted to put them on there, you totally could. I think in our last year's note sheet, we had a couple random things too that were like, oh, acids are sour and bases are bitter, and things like that. I mean, it's not overly important, but I think this is a great list. We have both definitions, Arrhenius and Bronsted-Lowry. We reference pH. We reference phenolphthalein, which is the indicator that we use almost always. And then we also reference just the generic setup of what an acid-base reaction looks like. Pretty good list, okay? Let's move forward. I just want to get our brains in the right mode. Okay, so what are the names of HCl and HClO4? Now, do I expect you to know one of these offhand? Yeah, I think so. Do I expect you to know the other one offhand? I kind of doubt it. But if you go beyond 4.9, right, the next sheet after 4.9 in your packet is the acid-base note sheet. If you want to have that out today, or if you have your packet, if the staple's out of there, or even if you want to tear that out of there, I don't care. But you probably want your acid-base note sheet somewhere nearby because it will help a ton. So what are the names of HCl and HClO4? What's the name of HCl? This is called hydro. chloric acid. HClO4, what's that one? Perchloric. Acid. Okay? Write the dissociation for HCl and HClO4. What you're going to do is I have HCl aqueous on the reactant side. And on the product side, I'm going to break it apart. I have HClO4 on the reactant side. And on the product side, I'm going to break it apart. Go for it. Shouldn't take you too long. What do you get when you have your strong acids and they break apart? You get H1 plus, and you get whatever else is there. Okay, easy peasy. What are the formulas for sulfuric acid and hydrobromic acid? What are the formulas for nitric acid and hydroiodic acid? Write them all down. They should all be on your note sheet. Some of them you might not need to look up, some of them you might. What's sulfuric? H2SO4. What's hydrobromic? And that's the same structure as hydrochloric, right? We're just changing out the chloric for a bromic. In other words, chlorine and bromine, but same formula, same structure. What's the formula for nitric acid? And what's the formula for hydroiodic acid? Now, hydroiodic, hydrobromic, hydrochloric, all from the same family, all same structure in its name, HCl, HBr, HI. Nice and easy. What's unique about these six? On this slide, I have 6 acids. What's unique about these 6? These are our strong acids. Okay? If it's not one of these 6, it's weak. What we need to start being able to do, hopefully, okay, is we need to start being able to recognize when an acid is strong or weak. We have to start being able to pick that out in a chemical reaction. The best way to do this is remember or memorize the 6 strong acids. If it's not one of the 6 strong acids, it's a weak acid. You know what I'm saying? Like, well, remember these 6? We're good. Anything else we see, weak. Make sense? So, hydrochloric, hydrobromic, hydroiodic. The one you've got to be careful with is hydrofluoric, which is also from the halogens, right? Hydrofluoric acid is a weak acid. It's the only acid from that family, I guess, if we go beyond iodine too, right? But it feels like it wants to be a strong acid because all of its friends are strong acids, but it's not. Hydrofluoric acid is weak. Okay, so be very careful about that. The other ones then, nitric, sulfuric, and perchloric. I don't know if they're the great. I think sulfuric and nitric, you maybe have heard of those in your life, or just kind of not necessarily in chemistry acids. Like those are generally like the very bad acids that get used for like science fiction and television shows and stuff like that, right? Like, oh, they're using nitric acid. Like, oh, that sounds bad. Okay, it's a strong acid. But perchloric, I don't know. So somehow, some way, however you want to memorize these, if you memorize these 6, it makes your life easier because then we know, okay, yep, it's one of the 6. Boom, it's strong. Or, oh, it's not one of those 6. Okay, I don't have to think anymore. Okay. All right, so let's keep going. Maybe, there we go. Show the reaction for how ammonia behaves like a base. So ammonia is a base. However, it's like one of the bases that it's one of the few bases we used last year that doesn't have hydroxide in the formula. Okay, and that makes it more difficult to realize it's a base. Ammonia is NH3. And in order to prove that it's a base, or to show you that it's a base, I'm going to add it to water. Sorry, I suppose this would not be aqueous yet then. Ammonia is a gas at room temperature, by the way. Okay. When ammonia gets added to water, what happens is the ammonia will behave like a Bronsted-Lowry base, meaning the ammonia will accept a hydrogen. What's it going to accept a hydrogen from? The water. So the water is going to give one hydrogen to ammonia, and let's see what we get as products. When I move one hydrogen over, I get NH4, 1 plus, which is called ammonium, and I also get OH, 1 minus, which is, of course, hydroxide, and this is why ammonia is a base. Okay, so ammonia itself does not contain hydroxide. But when I mix it with water, essentially it takes a hydrogen from the water to produce hydroxide. Make sense? So it's kind of weird. It's using both definitions. It's accepting a hydrogen, that's Bronsted-Lowry, but it's also a substance that when I throw it in water produces hydroxide. That's Arrhenius. Okay, so those definitions, again, have some crossover. They're talking about the same substances. It's just how we define it. And ammonia is definitely a base. Now, let's look at a funkier one. Show how the reaction of diethylamine behaves like a base. You have no clue what that stuff is. I'm assuming. That feels like a safe assumption. Here's the formula for diethylamine. It is C2, H5, 2, NH. Would I expect you to know that? No. Do I want you to learn that? No. Okay, if you get asked a question with diethylamine on the AP chemistry test, they're going to give you that formula. So I don't care about that part, but here's what I do care about. We need to show how this is a base. We're going to do the exact same thing we just did with the ammonia. Okay, I have this compound with water, and what's going to happen is the water is going to donate a hydrogen over here, and this molecule will accept it. And I'm going to get C2, H5, 2, NH, 2, 1 plus, and OH, 1 minus. Okay. Now, this looks more complicated than the previous example, right? But there's very clearly a similarity here. What I have is a nitrogen group, NH3. A nitrogen group, and this one is NH. Sorry for moving. Okay. Nitrogen groups, NH3, NH2, NH, and N. These are bases. These groups of nitrogen will take hydrogen from water. When I mix any of these nitrogenous bases in water, they will produce hydroxide. The hard part is picking these suckers out, because this is not a formula we've ever seen before. And the next one I give you is probably a formula you've never seen before. So how in the world can I know that it's a base? I've got to pick out that nitrogen group. It might be an NH2, it might be an NH3, it might be an NH. But if you see some molecule with the nitrogen group, it's a base. It's going to behave like a base. It's going to take a hydrogen from the water, and it's going to produce hydroxide in the process. They're called nitrogenous bases. Okay, be on the lookout for them. We'll obviously do some practice and help you find them later, but Just want to make that aware. Okay, so I've given you that sentence down there, and hopefully we can start trying to pick those out because those are going to be tougher to pick up. All right. Write a neutralization reaction for the following. Cross off any spectator ions. Now, I have 3 examples right here. I would like you to try these, but here's what you need to be aware of in order to get these correct. If you have a strong acid, it breaks apart. If you have a strong base, it breaks apart. If you have a weak acid, it stays together. And if you have a weak base, it stays together. Okay? See what you can do. See what you can do. Got to make sure I took attendance for the 3 people. Important. Strong, dissociate. If it's weak, leave it as it is. Write out the formula just like you think you should. Strong, break it apart. If it's weak, keep it together. When you produce salt on the product side, it will always be aqueous. Always. Okay? So you'll make some water normally. If it's a Bronsted-Lowry reaction, we won't make water. We'll just transfer a hydrogen. But if it's an Arrhenius reaction, we will produce water and salt. The salt that we make will always be aqueous. It should be written dissociate. Okay? Let me do the first one here. I know you're still chipping away, and I'd like you to try the next 2 if you haven't tried the next 2. Hydrochloric acid, strong or weak? How should I write it? So I'm going to write H1 plus Cl1 minus. And I'm reacting this with potassium hydroxide, strong or weak? Potassium hydroxide, strong or weak? It's strong. How do you identify strong bases? I didn't talk about that yet, did I? Yeah, if you have a cation from column 1 or column 2 on the periodic table, in other words, any element from column 1 or column 2 with hydroxide, it's a strong base. Any other base, not strong. There's one exception to that. Beryllium hydroxide is a weak base. It's the only weak base with hydroxide in it. Okay, but I will never use that, and neither will AP, because it just is a wrinkle of confusion that doesn't need to be made. So I won't use it. So you don't even have to be on the lookout for that. But potassium hydroxide is strong, so we should write this dissociated. Okay, here's my acid, and here's my base. Strong, strong. What happens? Well, I get some water, because the H and the OH make water. And I get some salt. The salt is going to be the combination of the other cation and anion from your acid and base. So the salt here is going to be potassium chloride. But the salts that we produce from acid-base reactions will always be aqueous. And if it's aqueous and it's ionic, which it is, it's a strong electrolyte. So we keep it dissociated. So I'm going to get KCl, but I'm not going to write it like that. I'm going to write it as K1 plus and Cl1 minus. And where am I at? Well, what did the chlorine do? Nothing. Okay, chlorine did nothing. There it goes. Potassium also did nothing. There it goes. What's the reaction? What am I left with? H plus OH equals water. That is the net ion. Okay. Remember, net ionic, we cross off any spectator ions, any ions that just don't change or do any chemistry. Next one. Okay. Try it. If you have not tried it, please try it. And if you're good at that one, do the third one. And if you're good at that one, hey, look, there's a fourth. How exciting. Try these by yourself if you could, please. I would rather have you try them than you watch me do them. I know what I'm doing, at least most days. I know what I'm doing, and watching me do it is not going to help you. Please try it. Some days I'm very confused as to what I'm doing. That's usually not chemistry related, though. It's more like quarantine, COVID life related. Like, how can I entertain my children this evening? Difficult question. It's strong, break it apart. If it's weak, keep it together. Hydrofluoric acid, strong or weak? It's weak. It stays together. Lithium hydroxide, strong or weak? Strong. Break it apart. These react. And what do we get? We get water. And we get salt. The salt is going to be lithium fluoride. But any salt we produce in an acid-base reaction is aqueous. And it's ionic. And it's dissociated. So we'll write our salt as lithium 1 plus and fluoride 1 minus. Okay, let's look for spectators. What did the lithium do? Nada. Didn't do anything. There it goes. And our net ionic equation this time is HF plus OH gives us water and F1 minus. Okay. Keep going. Try the third, try the fourth if you have not. This is something you need to be able to do in this class. Take written words of acid-base reactions and turn them into formulas and equations. Acetic acid, strong or weak? A weak acid. Now, the formula for this one is probably something you wouldn't have memorized, I wouldn't think. Okay, this is vinegar, by the way. Okay. Acetic acid is the acid of an acetate ion. So acetate is one of your polyatomic ions, C2H3O2, 1 minus. This, as an acid, is H, C2H3O2. That is acetic acid. Vinegar. Okay? It's weak. We keep it together. Oh, oh boy. That's exciting. All right. Try again. Ammonia, strong or weak? Weak. It is what it is. Uh-oh. What do I get as products? Water and salt, right? But uh-oh, this is Bronsted-Lowry. Okay? If I don't have OH, which I don't, I can't make water. This is a Bronsted-Lowry reaction. Instead of making water and salt, what we're going to do is move a hydrogen from the acid to the base. What's the acid? Well, the one that says acid. Pro tip. Okay. What's the base? Well, the other one. All right, good. So this is going to donate a hydrogen to that. Now, you might be asking yourself, well, there's one there, and then there's 3 more later. Okay, this throws people for a loop. When we write out formulas for acids, only the hydrogens out front are what we call acidic. This is an acidic hydrogen. In other words, this is a hydrogen that can be dissociated, or this is a hydrogen that can be donated. These 3 are not. If they were, we would write the formula with more hydrogens out front. So whenever you see a formula for an acid, it's just these initial or the first hydrogens. This could be H or H2 or H3, but it's only the ones at the front end of the formula that are acidic. Okay? So these 3 are just going to stay together. This is a polyatomic ion. Our polyatomic ion is going to stay together. I'm going to take this hydrogen, toss it over on the other reactant. This is the donor, this is the acceptor, this is the acid, this is the base. And as a result, I get C2H3O2 with a 1 minus charge, aqueous, and I get NH4 with a 1 plus charge, aqueous. Any spectators? Nope, it all stays. Everything's changed, right? There's nothing hanging around doing a whole lot of nothing, right? It's all good. That's it. Last one. Hydrobromic, strong or weak? Strong, so I should write it dissociated. H1 plus, Br1 minus. Ammonia, we already discussed that one. It's weak, is what it is. You can write it as it is. Okay. Again, I don't have hydroxide, right? This is Bronsted-Lowry. When I don't have hydroxide, I can't make water. So I'm just going to move a hydrogen from the acid to the base. Well, this is the acid, right? It's dissociated, but it is the acid. These two combined are my acid. This hydrogen is just going to get added to the base. That's all. Let's do that. What do I get? I'm going to get Br1 minus. That didn't change. It's going to be a spectator. And I get ammonia, NH4, 1 plus. And what do I cross off? A spectator here. Use like every color. Yellow. Ketchup and mustard. And that's kind of it. Now, what do you need to know? How do you do this? You look for strong or weak, right? Strong, break it apart. Weak, keep it together. Products. Sometimes it's water and salt. Sometimes it's just salt. By the way, this is a salt. Ammonium acetate is an ionic compound. So it's still making salt. Okay, the water for a Bronsted-Lowry reaction is just kind of implied, kind of there. We don't write it out as a product, but obviously this is all in solution, right? It's all aqueous, so water is still very much there. Okay, so we still generally say water and salt are the products for acid-base reactions. The salt is still there. This is ammonium bromide. Okay, that's an ionic compound. It's a salt. Any questions before I get away from the whole non-ionic acid-base stuff? Okay. All right, now we're going to pick up the pace a little bit. Okay. After this table, we'll pick up the pace. How's that? We'll go back to red. No, we won't. Okay. Hydroiodic acid, when is it strong? Or when would I dissociate it? What phase of matter am I looking for? When would I dissociate hydroiodic acid? What phase of matter? Your phases of matter to choose from are solid, liquid, gas, and aqueous. When do we dissociate strong acids? Aqueous. Okay. So when is hydroiodic acid strong? Well, it's strong when it's aqueous. When is it weak? When would we not dissociate HI? When would I keep that formula together? Anytime else. Yeah. If it's solid, liquid, or gas. Okay? If it's solid, liquid, or gas, that formula stays together. If it's aqueous, I break it apart because when it's in water, it dissociates. It's strong. When is it concentrated? Do you remember the terms concentrated and dilute? Okay. What is a concentrated solution? What is a dilute solution? We had a cutoff of what we called concentrated. Anything above that was concentrated. Anything below it was dilute. Do you remember what that cutoff was? It was a nice number. Yeah, it was 1. Okay. When is this concentrated? When the molarity is greater than 1. When is it dilute? Well, when the molarity is less than 1. And that is true for any solution. So I have 3 more examples in this table. When are any of these concentrated? When their molarities are bigger than 1. When are any of these dilute? When their molarities are less than 1. That's just a generic description of its molarity, right? You can call any solution concentrated or dilute just by looking at the molarity. It doesn't have anything to do with the type of solution. It doesn't matter if it's strong or weak or whatever else. If it's over 1, it's concentrated. If it's less than 1 for a molarity, It's dilute. All right, so when is ammonia strong? Never. When is it weak? Solid, liquid, gas, or aqueous, right? Ammonia is weak, even when in water. It's aqueous. Hydrofluoric acid, when is it strong? Never. It's a weak acid. When is it weak? Solid, liquid, gas, aqueous. Calcium hydroxide, when is it strong? Aqueous. This is a strong base, right? But when would we break it apart? Or when would it show that it's strong? Or when would it show itself dissociated? It has to be in water. When would it be undissociated? When is it weak? I'll put in quotes. Solid, liquid, gas. Okay? So here's the key takeaway with this little chart that was quick. When something is strong, it only dissociates if it's in water. Otherwise, if it's in its pure form, solid, liquid, gas, it's undissociated. Okay? When do weak acids and bases dissociate? Never. Okay? Or I should say, we don't write them dissociated ever. Okay? Even when they're aqueous, these stay together. And then concentration, right? When is it concentrated, when is it dilute? That's a molarity of 1. Bigger than 1, concentrated, less than 1, then. Cool? All right, let's keep going. Write the balanced net ionic equation for hydrofluoric acid reacting with ammonia. Go for it. We're using it in a different context this time, though, okay? So I know I've asked you to do like 4 of these already, but this one we're going to use a different context with. Hydrofluoric acid, strong or weak? Weak. Keep it together. That's just good life advice. Okay, ammonia, strong or weak? These react. What do we get for products? Get F1 minus, aka fluoride, and you also get NH4 1+, which is ammonia. Okay, the order doesn't really matter. I put it in plus minus just because. All right, but here's what I want to do. Okay, on each side of this of the arrow, there is an acid and there is a base. Okay, on both sides of the arrow, there is an acid and there is a base. What's the acid on the left side? What is the acid on the reactant side of my reaction? Hydrofluoric, HF, right? That's the acid. I'll put an A. What's the base? The other one, ammonia. Okay. How could I know that? How do I know to identify this as the acid and that as the base? Yeah, the acid is going to have an H in the front, right? So this one has an H in the front. All right, that must be my acid. That absolutely works. Here's another way. Bronsted-Lowry. This one gave up a hydrogen. This one accepted it. Acids are proton or hydrogen donors. Bases are proton or hydrogen acceptors. Because when I look at the products, right, I can see, oh, that one accepted it. This one donated. Right? Another one. Now let's go to the product side. Which of these two is the acid? And which of these two is the base? 50-50 shot. Okay. What is the acid? Is the ammonium or the fluoride the acid on the product side? even if you're wrong. 50-50. Gotta be. What is the acid? What is the base over there? Are you thinking, or are you just waiting for me to bail you out? Your eyes are smiling. Are you waiting for me to bail you out? Thank you for your honesty. Come on, somebody commit, go. What's the acid? Say it. You're wrong. Okay, so, thank you. That's all I wanted, just a commitment. But it's wrong. Naturally, it always never fails, right? When I say 50-50, it seems like the kid always gets it wrong. I do apologize. Okay, so the acid is actually the ammonia. Now, I'm going to put Ca and Cb. That stands for conjugate. Okay? There is something called a conjugate acid and a conjugate base. Now, let me explain why these are what they are. Okay? If you were to run this backwards, okay, if instead of running the reaction this way, if I ran it that way, okay, which of these would donate a hydrogen to the other? The ammonium would donate a hydrogen to the fluoride, which means this is the donor, that's the acceptor. Based off Bronsted-Lowry's definitions, things that donate are acids, things that accept are bases. Okay? So that you can look at it like that. The other way is this was my acid, and its conjugate base is what it turns into after it donates a hydrogen. This is my base. Its conjugate acid is what it turns into after it's accepted a hydrogen. Okay? They're paired up. This is a conjugate acid-base pair. This is a conjugate acid-base pair. Their difference is by one lonely hydrogen. Here's the acid. After it donates, here's its conjugate base. Here's the base. After it accepts, here's its conjugate acid. Okay? These are called conjugate acid-base pairs. Let's fill out the bottom, and then we'll call it a day. I got 2 minutes. Okay. The acid on the right is the conjugate base, or sorry, the acid on the right is the conjugate acid of the base on the left. The base on the right is the conjugate base of the acid on the left. Okay. In other words, kind of like I just said, there's the acid, it donates, and now it turns into its conjugate base. There's the base, it accepts, and it turns into the conjugate acid. Okay, we'll pick this up tomorrow. People at home, thanks for joining me. I appreciate it. Let's sanitize really quickly, and we'll pick this up, and we'll finish this 4.8 stuff tomorrow.